Hi everyone. So today we're going to be looking at the first section of medical imaging, which is using X-rays. Imaging is generally a term used to describe any method that allows us to view inside of a human body without any invasive surgery. So we'll be looking at ultrasounds, X-rays, CAT scans, PET scans, and so on. But our focus for today's lesson, the first lesson, will be using the X-rays and how we can use them. And so we'll be focusing on the basic structure of an X-ray tube, how X-ray photons are produced from an X-ray tube, the X-ray attenuation mechanisms, the equation that we can use to calculate how the intensity of X-rays changes, and how contrasting media are also used in X-ray imaging. So we're going to start first with a quick reminder of X-rays. That's part that you have learned in the waves chapter 11. So what X-rays? They're electromagnetic waves that travel at the speed of light. They can be diffracted, plane polarized. They have extremely short wavelengths. So remember that you do need to know the range of wavelengths for all EM waves. So this is a bit of a reminder from that. They're harmful to living cells that can kill them. They also consider as photons. So we're going to be talking about X-ray photons mostly, or beams of X-rays. And also you from quantum physics, so that was chapter 13, you learned about the energy of a photon is equal to the Planck's constant times the frequency of the wave. In this case, we're interested in the frequency of X-rays, and we can rewrite that expression as this expression, since we know that the speed of light is equal to frequency times wavelength. You can rearrange for frequency, and you just substitute that in there. So that will be E is equal to hc over lambda. So if we compare a photon of light with a photon of X-ray, just to remind you again from your prior topics last year in your AS content, that the gamma rays have the highest frequency and radio waves have the lowest frequency, but the highest wavelength. So remember that part. So a photon of light has a lower frequency than a photon of X-ray. So that since energy is directly proportional to the frequency of the wave, then obviously the X-ray will have the highest frequency and hence the highest amount of energy. So we will be looking at how X-rays are produced. X-rays are always produced in an X-ray tube. So here is an X-ray tube inside the equipment. Here you have the photographic plate. They use digital photographic plates now, so they can store the images that they take from an X-ray. And what you have are the beams of X-rays passing through the hand. Some obviously get absorbed, and then you created an image through on the other side of the photographic plate. So this is an X-ray tube. I will talk through how you need to know how an X-ray tube works. You need to know all of its components and how the X-rays are actually produced in an X-ray tube. So a few of the key features is that you always have a really high voltage between the anode and the cathode. So your cathode is here, your anode is here. So this is the metal, that's your anode. We call it the target metal. It's usually tungsten, made from tungsten, the element. And this is your cathode. So between the anode and the cathode, you have a really high voltage, about 30 to 100 kilovolts. So I'll write that down. This is the range that they use in hospitals for a normal X-ray. So that's the high voltage between the cathode and the anode. The whole setup is lined with lead, so that it prevents any X-rays from escaping towards the radiographer. It's also in vacuum, so that's for the electrons not to interact with any gas atoms or part molecules. And you have a window where the X-rays will be coming out from. And yeah, that's it. Basically, your filament is going to be your cathode, so that's connected to a different low voltage supply to begin with to heat it up and release electrons through thermionic emission. So what we have there is the electrons being released through thermionic emission. Those electrons are then accelerated through this high potential difference between the cathode and the anode. So they're accelerated towards the target metal. The target metal usually used is tungsten that has a high melting point. So the X-ray photons are actually produced when the electrons are decelerated by hitting the anode. So what you have is the electrons hit the anode and all the kinetic energy that the electron had gets converted to thermal energy or transferred to thermal. And part of that kinetic energy that the electron had also gets transformed into an X-ray photon. So it's one electron for one X-ray photon. Also, another key feature that you do need to know is that since obviously a lot of that heat, a lot of thermal energy is given to the target metal, it needs to be cooled down. So they usually circulate oil on the anode to cool it down, or they spin or rotate the anode to spread the heat over a larger surface area. And they also have the anode shaped so that the X-rays are emitted in the correct direction through a window. Otherwise, the X-rays would be emitted in the wrong direction and you wouldn't be able to take it. So that's why it's angled in that direction if you look at the anode. Okay, so far we have spoken about the basic structure of an X-ray tube. We looked at the heater, which is the cathode. We talked about the anode, which is the target metal, and how there needs to be a high voltage supply between the cathode and the anode. We also spoke about the production of X-ray photons from the X-ray tube in terms of the electrons being decelerated so that the kinetic energy of the electron gets transferred to thermal and the rest of it as an X-ray photon. We will look at the mathematical analysis of this part, and then I will move to the X-ray attenuation mechanisms. Okay, so another way, before I move on to the mathematical analysis, another way that the photons X-ray photons can be emitted from the target metal is when that incoming electron hits the target metal, it will remove one of the electrons, so it will give it enough energy. So this is a tungsten atom. So what it will do, it will remove one of the electrons completely. Once the electron gets removed, another one from a higher energy level will move back down to take its place. And that movement from a higher energy level to a lower energy level releases a photon, because that extra energy is being released as an X-ray photon. So that's another way of X-ray photons being produced. Now, if we do the maths for it, we know that And we have seen this, by the way, quite similar method in the electron gun. So this is a topic that we've done in electricity in year 12. So if we have a potential difference and we're accelerating an electron, we can calculate, or a charged atom or ion, then we can actually calculate the energy that that charged particle will have if it's accelerated through a potential difference. And to remind you that potential difference is defined as the work done per unit charge. So the work done, or the energy that the electron will have, will be potential difference times charge. So that will be the charge of an electron is E, and the potential difference between the anode and cathode is V. So that's how we can calculate the energy of the electron accelerated through a potential difference V. Now, if I want to know the energy that the photon will have due to this electron, so the X-ray photon will have, we already mentioned in the previous part that you need that one electron will have the same, the energy that the electron has will be the same as the energy of the X-ray photon produced. So we also know that the energy of a photon can be given as HF. So that's HF is equal to EV. Planck's constant times, remember this is Planck's constant, this is frequency, this is the charge of an electron, this is the potential difference. And if we want to link it to the wavelength of a photon, of the X-ray photon, then we just simply substitute C over lambda for this one. I explained already at the beginning of the video, so you already know about that one. C over lambda is equal to EV. And if you want to find the wavelength, then that would be HC over EV. So if I increase the potential difference that accelerate the electrons through, what will happen to the intensity of the X-rays? So intensity is something that, again, you have seen in the waves topic in year 12. That's chapter 11. So intensity is the power per unit area that it passes through, or the energy, the rate of energy transfer per unit area of the wave. So that's an important part to link here. As you've noticed, there's a lot of synoptic links here from different topics, so quantum physics, waves, EM waves, and so on. So it's quite important to bring them all together. Okay, so what do we mean by attenuation mechanisms of X-rays, and how does that link to what we're learning? Since we're dealing with medical imaging, we need to be able to see clearly in someone's body without having to invasively, do an invasive procedure. So what you see here is just a simple X-ray of someone's shoulder and a bit of his lungs there. What you notice is the bones quite clearly stand out, quite white compared to the greyish black shades that you can see in the image. So that has to do with how different tissue absorbs or scatters the X-rays. In the picture, you can see that the air in the lungs appears quite dark because air doesn't absorb X-rays as much as bone does. And you can see the bones absorb the X-rays because you can clearly see the bone. And you have soft tissue that appears a bit grayish because it does absorb some X-ray photons, but not all. So X-ray photons, as they pass through the body, and depending on how much depth parts of our body have as well, it will be attenuated more and more. So what do we mean by attenuation? Firstly, before I proceed, attenuation is just simply the decrease in the intensity of the electromagnetic radiation as it passes through matter. And we will see how that equation works as well. We will also see firstly the different attenuation mechanisms. So just to restate, that as X-rays pass through a material, they are gradually absorbed, which will lead to the reduction of the intensity of the signal that goes through them. So which one attenuates X-rays more, bones or soft tissue, and why? This is what we will be answering quite soon. We know definitely that bones attenuate X-rays more, but you don't know the reason yet, and we will come across it. So I will be talking through four different attenuation mechanisms. So basically 4 ways that the X-rays intensity can decrease as it passes through matter. And it has to do mostly with how X-ray photons interact with the atoms. So in each mechanism, you're going to notice that the intensity of the beam of X-rays will decrease, and how that happens. So for the first one, a simple scattering. Now, this is for photons that have an energy range of 1 kilo electron volt, 1 kilo electron volt to 20 kilo electron volts. So an X-ray photon will have less energy than the energy needed, in this case, for an electron in an atom to be removed. So what you see in the picture is the incident photon that has less energy than the energy needed to fully remove an electron. So it will bounce off it, it will scatter, and no energy change will be observed in the scattered photon and the incident photon. This is called simple scattering or simple scatter. And this is when you have the X-ray photon that doesn't have enough energy to remove fully an electron, so it will be absorbed by the electron and then rescattered back as it does not have enough energy to release the electron. So there will be no change in the energy or decrease in the energy. This is not usually used in hospitals, actually. We already said that the potential difference used in hospitals is much bigger than that. So it's about 30 to 100 kilo electron volts. So you won't really use that in any radiography in a hospital. The second attenuation mechanism, which is actually the one that is seen in used in hospitals, because the energy of the photons are they're less than 100 kilo electron volts, and hospital X-rays use 30 to 100 kilovolts potential difference. So this is where you have this is what you have mostly taking place when you have an X-ray in a hospital. So the energy, like I said, needs to be less of a photon, will be less than 100 kilo electron volts. And what you see here is that you have an X-ray photon. So this is the X-ray photon in terms of wave. It gets absorbed by an electron, and since it has enough energy, it allows the electron to escape the atom. So this is the photoelectric effect. This is something that we have seen in quantum physics in chapter 13 in your first course year. And basically the X-ray photon gets absorbed, it has enough energy by the electron, so it will emit, the electron will escape, basically. So this is the second mechanism, and there's 2 more. So we have the third one. The third attenuation mechanism is Compton scattering. The photons will have an energy between 0.5 to 5 mega electron volts. In this case, the photon will interact with an electron. The electron will be ejected, but it will also, since this photon will have more energy, the incoming photon has more than the required energy to remove an electron. The rest of the energy will be released as a photon with less energy. In both cases, though, energy and momentum are conserved. So there will be no conservation laws are broken. So once again, you have the photon, the incoming photon. It has more energy than it needs to remove an electron. So it will remove the electron and the rest of the energy will be rescattered. The rest of the energy of the photon will be rescattered, but with a lower amount of energy. So yeah, there you have the decrease of energy. And then you have pair production, which are photons basically that have an energy of greater than or equal to 1.02 mega electron volts. In this case, the X-ray photons will interact with the nucleus of the atom. It won't do anything to the nucleus, but it will disappear. The X-ray photon will disappear and turn into an electron and positron. So here you have a pair production. You have a photon changing into positron and an electron. This is something that we have seen as well in chapter 24, 25, from what I remember. So in nuclear physics, basically. So it's another concept that you can see is synoptically linked to others. Now, these two attenuation mechanisms are usually used in therapy than imaging. So we spoke about medical imaging being a way of looking into people's body, but there can also be a way of therapy, of treating symptoms or problems. So I'm just going to mention it here only now, and then I will move on to the attenuation equation as well. But X-rays can also be used for therapy rather than just imaging. They have specialized machines that they call LINACs. So basically they're linear accelerators, and they use high energy X-ray photons like these ones. So these energies. What they tend to do is these photons will be used to kill off cancer cells, and they do so through these two mechanisms, through Compton scattering and pair production. So these are the methods used for therapy, so to treat cancer. Okay, so just to remind you, with all these different attenuation mechanisms, all have one thing in common. They have X-ray photons that interact with matter, and for three of them we've seen that this interaction leads to a reduced intensity of the X-ray beam or photon. Now, the transmitted intensity of X-rays depends on the energy of the photons and on the thickness and type of substance. So what we'll be looking at now is the equation for a given substance, for any given substance. If we know the energy of the photons, we can see that the intensity falls exponentially with the thickness of the substance. So I will go through this equation. So what we have is the transmitted intensity. So what has passed through a bone or an object. X-rays are also used to on objects as well, but that's another thing that we don't really need to look into now. So we have I naught is the initial intensity before any absorption. I is the transmitted intensity. Mu, it's a Greek letter, mu, it can be called the absorption coefficient or the attenuation coefficient. It means the same thing. And X stands for the thickness of the substance. So for a specific material or a tissue in the body, mu will be different. So the bones will have a different mu attenuation coefficient than, for example, bones and muscle will have. And X is for the thickness of that specific tissue in our bodies. So we're going to have a look at how firstly we can use contrast media, and then I will go into an example question. So we have already seen how easy it is to see through bones and differentiate it from soft tissue in the body. However, what if you wanted to look at soft tissue in the body, and since soft tissue usually have quite similar absorption coefficients, it won't be easy to differentiate between the different types of tissues if they have similar absorption coefficients. The only reason you can see bones quite easily from normal soft tissue is because they have very different absorption coefficients or attenuation coefficients. So we tend to use contrasting media for us to be able to see differentiate between soft tissue, such as iodine and barium. Now, the reason that iodine and barium are used is because they're relatively harmless and they have large atomic numbers. Now, soft tissue on average has an atomic number of 7. But barium and iodine have high atomic numbers of 56 and 53. And we know that the attenuation coefficient or absorption coefficient is directly proportional to the cube of the atomic number. So what they tend to use in hospitals is they will inject iodine if they want to see blood flow through different organs, because it provides that high contrast medium in terms of where the blood flows and the tissue that it passes through. And barium sulfate is used in the digestive system. It's this white substance that you usually take by mouth. That's just about it. So any substance that has a large atomic number and it's obviously harmless to our body will be quite good for imaging in terms of showing, for example, how unhealthy someone's heart is or how healthy it is. Like doing an X-ray of a heart is called angiogram. So for you to be able to get that X-ray, you can't normally get it through a normal X-ray. So what they do, they inject iodine into your circulatory system so that the blood vessels will show up clearly on your heart. Or they will have barium meal, so you'll have to take in barium, and that will go through your intestines, which will make the outline of the intestines very easy to see and see how that the surrounding tissue is affected by it too. So this is a bit of the summary. So I have spoken through the X-ray attenuation mechanisms, where we've seen the simple scatter. So that's when the energy of the X-ray photon doesn't usually get changed. We've seen the photoelectric effect, which is mostly used in X-ray imaging in hospitals, and Compton and pair production, which are usually used in therapeutic use of X-rays. We also introduced the attenuation of X-rays intensity equation, and the X-ray imaging with contrast media. So we talked about how barium and iodine can be used for contrast in X-rays. Okay, so this is an example to have a look at before we finish off for the first lesson. So here you have the attenuation coefficient of a patient's body tissue is 0.2 centimeters per centimeter. So mu is 0.2 per centimeter. So that's the unit for it. We usually prefer it to be per meters, but obviously we'll see how it works through the question. So it says at what depth, so depth meaning x, so thickness, at what depth inside the tissue will an X-ray be attenuated to 40% of the intensity of the incident beam. So we already know that I want I to be equal to 40% of I naught. And I'm not given I naught, but I definitely know that I have I naught. So that'll be 0.4 I naught. So we know that the equation is equal to I is equal to I naught e to the minus mu x. Here we already know that I will be 0.4 of I naught. I naught and I naught can cancel, because if I divide both sides by I naught, they will be removed. And so I have 0.4 is equal to e to the minus mu x. So this is where you bring back your knowledge from a logs or a len, and you take a len of both sides, so that will be a len of 0.4 is equal to minus mu x. I need to calculate x, so I will rearrange for x, so I will divide both sides by mu, minus mu. And you have now, goes with that, x is equal to minus ln 0.4 divided by mu, which in case mu here was 0.2 per centimeter. That means the value of x I will get, so the thickness, the depth will be in centimeters as well. So that will be equal to 4.58 centimeters, or just about, since we were given the values to one significant figure, about 4.6 centimeters. Okay, so I hope you found this useful, and I will be doing the second lesson on CAT scans, which are using X-rays. So that's the last part of X-rays that you'll see in the next lesson.